Okay, so modern nuclear physics is the next one, and it is ridiculous how many free response you have there, but they're not tough, so I'm going to do them, but I'm just going to do them on plain paper because the type is so crumped together that you can't hardly do anything off of this sheet. Alright, so I'm going to start out with 1989 B6. Let me make sure I'm not lying to you. Yep, 1989 B6. Alright, so I'll do them all. It'll take a while, but we'll get them done. It would be wise of you to look at them. So 1989 B6. Okay, so the problem says a lithium nucleus while at rest decays into a helium nucleus of rest mass blah 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 and a proton of rest mass blah 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 shown by the following reaction. In this reaction, momentum and total energy are conserved. After the decay, the proton moves with a speed of 1.95 times 10 to the 7th meters per second. So part A is very easy. It says, what in the world is the KE of that proton? So it's 1/2 m, and they give us m is 1.6726 times 10 to the minus 27 kilograms. And it's moving at a speed of 1.95 times 10 to the 7th meters per second. And I'm going to square that because it's 1/2 mv squared. And when I did that, I got 3.18 times 10 to the minus 13th joules. 3.18 10 to the minus 13th joules. So that was easy, very easy. That's just a 1/2 mv squared situation. Okay, B says determine the speed of the helium nucleus. So I think we're looking at some kind of a conservation of momentum, is what my little brain says. So the momentum before equals the momentum after. So I said m of the proton, velocity of the proton, equals m of the helium nucleus, mass of the helium nucleus, velocity of the helium nucleus. So this was my 1.6726 times 10 to the minus 27th kilograms, moving at 1.95 times 10 to the 7th meters per second. And that is equal to the mass of the helium nucleus, which they told us was 6.6483 times 10 to the minus 27th joules, kilograms, times the speed. The speed of the helium nucleus is going to wind up being 4.91 times 10 to the 6th meters per second. So that was good. Alright, C said, what is the kinetic energy of the helium nucleus? So I did KE equals 1/2 mv squared. Don't forget to square it. And so when I did that, I got 8 times 10 to the minus 14th joules. So everything's looking good so far. Alright, then I went on to D, and D said, determine the mass that is transformed into kinetic energy in this decay. Alright, so I knew that I had 8 times 10 to the minus 14th joules, and I had 3.18 times 10 to the minus 13th joules, so that was the amount of energy that was made available. Alright, now let me go back and make sure I'm not telling any lies. No, I'm good. So when the lithium fell apart, it had some helium that was given off, and or an alpha particle that was given off, and a proton that was given off. And so that's the energy that was received. So that energy is going to equal to mc squared. So when I did that math, I was able to determine the mass that was transformed into kinetic energy, because that was my two forms of kinetic energy. And when I did that, my mass was 4.42 times 10 to the negative 30th kilograms. So that wasn't any big deal. And then there was an E, and it wanted to know the mass of the lithium ion. Well, the mass of the lithium ion is going to be equal to the mass of the alpha particle, or helium, whatever you want to call it, plus the mass of the proton, plus the mass that was converted into energy right here. So the mass of the helium, they told me, was 6.6483 times 10 to the negative 27 kilograms. Mass of the proton was 1.67 times 10 to the minus 27 kilograms. And it actually was 1.67 times 1.6726. So I left a few numbers out, but you got it. And this was 4.42 times 10 to the minus 30th kilograms. So these three masses had to have come from that lithium. So when I added those up, I got the mass of my lithium to be 8.3253. And I report all those decimals because they didn't tell me how far out to take it. So there's my first one. All right. Got quite a few more to go. 1, 2, 3, 4, 5, 6, 7 more to go. Okay. All right. So my next one was 1996 B5. All right. So it says an unstable nucleus. I'm going to call that X. Yeah, X is good. That is initially at rest, decays into a nucleus of fermium-252. And it has 100 protons and 150 neutrons, so that's where that plus the 152 gave me the 252. And then I have an alpha particle, and you have to know that an alpha particle is 42He. And then you have, is that all you have? Kind of looks like it's me. All right, so they want to know what the atomic number of this one is. Well, if that's 252 and that's 4, I said, well, I'm thinking that 252, and actually, this is kind of stupid of me. I'm sorry. I apologize. I think I'm all right. Okay, so that's going to be 256. That'll be the mass number. But this will be 102, and that's what they want is the atomic number. Okay? All right. So atomic number was 102. That was part A. Piece of cake. Part B says, what is the velocity of the alpha particle? Well, they give me the kinetic energy. They give me 8.42 times 10 to the 6th because it's mega electron volts, and they want to know the velocity. So I'm going to convert that from electron volts into joules. So there's 1.6 times 10 to the minus 19th joules for every 1 electron volt. So when I did that math, I got the kinetic energy to be 1.3472 times 10 to the negative 12 joules. All right, but before I can get a velocity, I got to do something with that lovely mass that is in atomic mass units. And they want to know the velocity of the alpha particle, so I go back up to my problem and I look up the mass of the alpha particle. Well, it's 4.00260 U's. But I got to get it out of use, so I say, well, that's 1.66 times 10 to the negative 27th kilograms for every 1 U. So the mass of my alpha particle was, let me see if I can read my writing, 6.64432 times 10 to the negative 27th kilograms. So now I have my Ke. I have my equation, Ke equals 1/2 mv squared. I know this quantity and this quantity, so I'm going to say 1.3472 times 10 to the negative 12th joules is equal to 1/2, have to have that mass in kilograms, 6.64432, 10 to the negative 27th kilograms, times V squared. So when I did my math, I got my V to be 2.01 times 10 to the 7th meters per second. So that was really more convergence than anything else. All right. Let's go to part C. Part C says, where does the kinetic energy of the alpha particle come from? Well, conservation of energy. I said that when the unstable nucleus decayed, fell apart, whatever you want to say, energy from, let's call it binding energy, from the nucleus was released. And that was the kinetic energy that they were talking about. All right. D says, assuming all the energy released in the reaction is in the form of Ke, so they really answer part C by giving the information for D. Determine the exact mass of the original unstable nucleus to an accuracy of 0.003 of a decimal. Okay, well, that's no big deal. Mass of Z is equal to the mass of the fermium. I think I call that X up there, so let's call that X. Mass of fermium plus the mass of the helium or alpha particle plus that M that was the mass defect. All right. So I said, well, this was, and there's a whole lot of ridiculous numbers, 4.185 10 to the minus 25th kilograms. Yeah, I had to convert my U's into kilograms. That was 10 to the 25th kilograms. The mass of the alpha particle we just said was 6.64 times 10 to the minus 27th kilograms. All right, and then we knew from our hang on, let me stop for a minute. Okay, so then I have to find that little M. Well, that mass defect had an energy of 8.42 mega electron volts. And there's a conversion on your chart of 900, I think it's 931. I think I better write that correctly. 931 mega electron volts for every 1 U. So if I divided those, I would get 0.009 U's. So when I added those all up, I got 2, and you'll have to, okay, I can't leave that in U's. Well, I guess I could if I knew these all in U's, and I think I do. So hang on, I'm having some. Okay, do you see what I did wrong? These are kilograms, kilograms in U's, so let's get this fermium mass in U's, and they gave it to us as 252.08249 U's. And then they said that the alpha particle was 4.00260 U's plus 0.009 U's from the mass defect. So now, finally, I can go back and say, well, that should be about 256.094 U's. So there's the mass of my unstable nucleus. Alright, so now let's see what else is left to answer. So let me pause again. Okay, so it says, suppose that the fermium-252 nucleus could undergo a decay in which a negative beta particle was produced. How would this affect the atomic number of the nucleus? Explain briefly. Alright, so I'm going to go down a little more. Alright, so if I had a negative beta, when you have negative beta decay, a neutron turns into a proton. So let me write that down. A neutron, which is really a proton and electron, turns into a proton. Proton, and releases an electron beta particle. So our unstable nucleus, X or Z, whatever we called it, will gain one more proton. So it's atomic number will go up by 1, so instead of being 102, it'll now be 103. All right? Okay.